Thank you very much. Well, yes, it's me again. And now I'm going to speak about this nebula, CRL 618. And well, this is the work that I did in collaboration with all these people whose names are written there. So, well, I will go straight to give a short introduction of this source, even though it's already very famous, but I would like just to mention that it was discovered on a survey with a rocket that they were searching for infrared emission at this wavelengths, 4, 11, and 20 micron. And it was first studied by Bill Westbrook, and that's why it is sometimes called the Westbrook Nebula. In his paper, like one of the main conclusions was that this object may be a planetary nebula seen in an unprecedentedly early phase in its evolution. Later on, molecular observations towards this source reveal the existence of large amounts of molecular material around the nebulosity, and the conclusion was that this source may be a protoplanetary nebula, so an object that is in a transition from HV star to planetary nebula. Later on, observations of the radio continuum revealed that actually the ionization of the gas had already started, and the conclusions of this work was that it was already an extremely young planetary nebula. So it was really the status of this star was really evolving very quickly as the years passed. So around 1977, they were talking about ionization in this nebula, and by 1981, some Kwok discovered that the radio continuum was the flux of the radio continuum was increasing very rapidly. In just a few years, the radio continuum emission increased by a factor of 2. So they, as I mentioned before, they concluded that it was evolving very quickly. And by 1984, they could obtain the first radio images of this nebula, and then in this work, they concluded that the radio continuum emission was coming from a very small region in the core of the nebula. But by 1988, Martin Pintado and collaborators, they found that the spectral energy distribution could be better modeled as an ionized stellar wind. So if this star was still losing large amounts of material in the way of a stellar wind, then one could ask the question whether this is really a planetary nebula or what kind of object it is, because still losing lots of material. Then the HST came and took very pretty pictures of this nebula, and actually of the bipolar or these finger-like structures around this nebula, and most of people forgot about the central part because these are very pretty, so they got more interested in the outflows. So, but we realized that in the VLA archive there were plenty of observations, and many of them were not published yet. So we decided to do all these observations and study the evolution of the ionized region, which is in the very central part of this bipolar nebulosity. So we could obtain from the archive, we And at one epoch, 1998, we could get observations at basically all the frequencies that the PLA can observe. Well, basically these are the characteristics of the observations, the epochs, the calibrators, and stuff related to the observations. And these are the results. We traced the increase of the radio continuum flux at two frequencies, 22 gigahertz and 5 gigahertz, for a time spanning basically 30 years. And well, as you can see, the radio continuum flux is obviously increasing, and also, since we have images of this object, we could also measure the size as a function of the epoch. And well, it turns out that the morphology of this source is like an ellipse, and so it has like a major axis and minor axis. So this is the evolution of the major axis, and this is the minor axis. And then we had all this information. We had all this information that the flux is a function of time at two frequencies, and the size is a function of time. And so we did a simultaneous fit to all this data that we had, and then we obtained an initial time for the ionization around 1971. So, well, it's just a picture showing how that from our results this is looking kind of weird.
I don't know if that's control the audio.
It's fine, I think.
Just put the mic a little further down here.
Yes, like this. So, as you can see here, the morphology of this nebula is kind of like elliptical, and the in the direction of the major axis is expanding, or the increase of the size is larger than as a function of time than in the minor axis. And also from our multi-frequency observations, we could get the spectral energy distribution at all the frequencies that we observed, and the size as a function of frequency. And as you can see here, the major axis as a function of frequency changes, while the minor axis remains more or less constant. So what it implies, this behavior, is that in the direction of the minor axis, the H2 region is ionization bound, whilst in the major axis there is a gradient of electron density. And actually this can be seen more clear in this spectral index map, in which we have combined the information at different frequencies. And so here the colors is the spectral index. So basically in this band, the kind of equatorial band, the spectral index is around 2, which means that the region is optically thick in this region. And as you move away along the major axis, the emission becomes optically thin at different distances. So we can use that information to actually obtain a profile of the electron density along this axis, and we find this profile, which is represented with this power law, the r to the minus 2.4, and we can model, or we can, if we assume that there is mass loss, kind of isotropic, like originally the mass loss follows an r to the minus 2 power law, then this power law that we're finding here means that the mass loss rate has been increasing for some period of time, that actually for our calculations since we have a limited size of the nebula, we found that in the last 100 or 130 years, the mass loss had to increase from 4 times 10 to the minus 6 to 6 times to the minus 6 solar masses per year. And this plot shows some results on a radiative transfer model of the radio continuum. And here we can see that we can fit very well the spectral energy distribution at 2 epochs using the geometry that we found and the electron density profile. So, but the question is why CRL 618's morphology is bipolar. Well, then it turns out that the Bruce and his collaborators, they have been observing this nebula as well, and they get, yes, they see that these fingers show some expansion, and actually what is even more surprising is that the kinematical age of all the fingers is more or less the same, which is around like 100 years. Then the scenario that I actually am proposing, or that we are proposing for this source, is something like this. Around 100 years ago, there was some kind of explosive event that expelled material in a kind of a bipolar way, and it expelled like bullets that somehow are passing through the envelope of the HB. Then as these bullets are expanding very fast, then there was a mass loss process from the central star, and around 1971, the ionization of this wind that took place just after the explosion started to be ionized, this wind. And by 1998, this whole wind was ionized. And, well, this is kind of like what I imagine will happen in the future when the ionization, the ionization propagates through all these parts and it starts eroding the HB envelope, and it will create a planetary, bipolar planetary nebula like the ones we see a lot. And just I wanted to show you that this is an image at 7 millimeters and 3.6 centimeters of this planetary nebula. This is radio continuum, and to me, I think it shows like a kind of like a S-shaped morphology, and yes, it's kind of funny the structure when I see it on the computer. So yeah, well, it calls my attention that it has this shape. Actually, I don't have an explanation why this should be this way. And well, these are the conclusions. So basically, the ionization began around 1971, and what we are saying here is that this ionization will propagate, and then basically we are seeing we are seeing the birth of a planetary nebula. So I guess this is a very rare event, and I think that this is very interesting to follow up. So thank you very much.
Questions? Ursula, and then please.
I'm going to ask this before Ron does. So if this was...
That's hard.
But if this event that was so sudden was triggered by, say, periastric passage, that's what I'm saying, it's not a question, by a companion that triggered the outburst, eliminated my mass from the giant and hence moved it forward into its evolution such that the ionization front is going to go as well, and it's all seeming quite coincident, so that's something that should happen in such a scenario. And then of course you see this S shape, which is always kind of indicative of binarity. What constraints do we have on the presence of a potential companion from the observations of this? And there's so many observations of this.
Yeah, well, I mean, from the observations that I have done or that I have worked on, I don't have any like clear evidence other than this S-shape. Like,
but there's so many other observations as well.
So there are a lot of IR observations, but one star is so bloody bright that no companion has ever been found for
So
it.
we can't see anything. We can't say there's no white dwarf companion.
We can't say that there's nothing. We can just say there's one hell of a star there. And as best I know, it hasn't moved. That's about all we can say.
Here, looking at your time evolution for the whole evolution of the object, what would you say that is the reason for, from the first view to the second one, to have this bipolar section, since you have the other event, the explosive one, that there's nothing to do with a bipolar explosion?
Yes, actually, what I'm here proposing is that the explosion itself was bipolar. And I don't know, actually that is like the main question, what caused a bipolar explosion? But yes, here basically what I just wanted to say is that there was a bipolar explosion, and then the ionization obviously is propagating through that lower density material, and that's why the ionization is mainly taking place in that direction rather than the perpendicular direction. But yes, the main reason is still unknown, I think.
So we've run out of time. Hold your questions for the question period coming up after the next talk. Jesus Toala. So here we move into the X-ray part of the spectrum and talk about the way in which heat is transferred in and out of the hot bubble. Thank you.